What's up, Internet? Addison here. Welcome to Addison Academy, and today we're going to dive into a fun and challenging physics problem asking us what the tension in a cable here when there's multiple cables operating at angles. This is going to require an understanding of F equals ma, Newton's second law, free body diagrams, trigonometry, algebra, and system of equations. So all those things are coming together in this problem, which make it challenging and fun. Okay. So step one is to figure out what the question is asking us. The question is asking us what is the tension in the 60-degree cable. We're going to set ourselves up by success by going ahead and filling in the part of the answer that we know. The tension is equal to something, and forces are generally expressed in newtons, including here in this problem. So that's step one. Step two, start to understand the facts that we have. First step, what are the forces acting on this block here? Most obvious force is the force of gravity, F, gravity. We're also going to go ahead and calculate this. F equals mass times acceleration, so 95 times the acceleration of gravity is 9.8. Multiply those two things together and you get 931 newtons, okay? So we're well on our way. There's two other forces acting on this block. You can probably guess what they are. There's the tension force in this 60-degree cable. That's the force that we're trying to figure out. We're going to call that T1. You can call it whatever you want. And there's the tension force acting in this 30-degree cable, and we're going to call that T2. Now, the primary challenge of this problem is that these forces are acting in diagonals. Diagonals are tricky because they're difficult to combine to create a net force. The way of dealing with diagonal forces is fairly straightforward. You want to break them down into their y component, their vertical component, and their x component, their horizontal component. So we can do that now. Notice that when you add the vertical component to the horizontal component tip to tail, you end up starting in the same place as the tension force and ending in the same place as the tension force. That's how you know that these are correct component forces. Okay, so now we've broken down our two tension forces into their vertical and their horizontal components. Now we need to use trigonometry, specifically SOHCAHTOA, in order to figure out the magnitude of these component forces. Okay, so we're going to do that now. SOHCAHTOA, sine is equal to the opposite side over the hypotenuse. So this opposite side is equal to the sine of 30 multiplied by the hypotenuse, tension 2. Okay. Now to make our life a little easier, we're going to get the trigonometry out of these problems. Sine of 30 is equal to a half. So we could simplify this as 0.5 T2. Nice. Okay, how about the horizontal component? Well, cosine is equal to the adjacent side over the hypotenuse side. So the hypotenuse, T2, times cosine 30 is going to be equal to this horizontal force. Okay. Again, this is going to be more straightforward. If we just go ahead and simplify cosine 30 now, it's equal to approximately 0.866. That's going to be enough accuracy for us here in this problem. So the horizontal force is equal to 0.866 T2. Okay, the same trigonometric logic can be applied over here in this triangle. It's a 30, 60, and 90-degree triangle, the same way over here. So sine of 30 times the hypotenuse is going to be equal to this vertical component. So T1 sine 60 here, T1 sine 60, which if you simplify the trig is 0.866 T1. And this side here is going to be T1 cosine 60, or 0.5 T1. Okay, so now we understand the magnitude of the vertical components of these two tension forces and the horizontal components of these two tension forces. Now the key is to ask, is this block accelerating in any way? This block's just hanging here off these cables. It's not moving or accelerating, so the acceleration of the system is equal to 0. Now we know with our fundamental guiding light equation, Newton's second law, F net equals m times a. If the acceleration is 0, then the net force is equal to the mass times 0. Anything times 0 is 0. So the F net of this system is equal to 0. That's quite helpful because it means that these forces cancel out. Now, since the block is not moving in any way, it's not moving in the x direction, it's not moving in the y direction, then we know that the F net in the x direction, F net x is 0, as well as F net y is 0. Okay? So we're now going to break down the analysis in the x direction here and in the y direction separately. So let's start with the x direction. There are two forces acting laterally on this block, the horizontal components of the tension force. Since the F net is 0, if we add these two forces together, they should be equal to 0. In other words, since they're going in opposite directions, they have the same magnitude. So we can say that T2, the horizontal component here is 0.866 T2, so let's rewrite that, 0.866 T2 is equal to the magnitude of this other horizontal force, 0.5 T1. So that's our key equation in the horizontal direction. Now in the y direction, we can do the same thing. This downward pull of gravity must be equal to the combined upward pull on the block since it's not accelerating. Now we know the force of gravity is 931, so we can say 931 is equal to the combined upward force, which is 0.5 T2 plus 0.866 T1, 0.866 T1. Okay, at this point, we've really done the hard part. We've done the trigonometry. We've set up our system of equations. If you notice now, we have two equations with two variables. Algebra tells us we can solve a system of equations if we have two variables. We need two equations, and we now have that. We're solving for the tension in the 60-degree cable, which is T1. So we want to solve for T1 here in this system of equations. The easiest way to do that is going to be to replace T2, to substitute T2 with something in terms of T1. So let's go ahead and solve for T2 in terms of T1 by dividing both sides here by 0.866. If you do that, you get T2 is equal to 0.5 divided by 0.86 is 0.577 T1. Now I can substitute in, I know what T2 is in terms of T1, so I can substitute it in for T2, and I get 931 is equal to 0.5 times T2, which we now know is 0.577 T1 plus 0.866 T1. Now we can see we have an equation with only one variable in it. So with a little bit of algebra, we multiply 0.5 times 0.577 and add that to 0.866, and you end up with 1.155 T1 is equal to 931. Divide both sides by 1.155 to cancel it out here, and we get the tension, T1, or the tension in the 60-degree cable is equal to 806.1 newtons. So that's a brief overview, putting together a lot of components of math there, free body diagrams, algebra, system of equations, and trigonometry in one problem. I hope you enjoyed. If you have any questions or you want to work together, feel free to reach out. I love physics, I love math, I love science, I love learning, I love reasoning, and I hope you enjoyed this video.